Hello guys, I hope you enjoyed your one last weekend before it all goes down. So on Wednesday we shall have a lesson. I hope you can make it. I almost finished writing your final exam and almost finished grading. Right? So I would probably try to send you the final exam by Wednesday, probably even today. I will at least will try today. I can promise, because every time I write it, I think like a kid in a candy store. There are just so many things to ask, so many, and I want to give you the nicest parting basket, so to speak, that I can possibly come up with. Yes. So the final exam will have to be due at the latest by the 25th of May, because they forced me to submit grade by the 28th. And yeah, so that the latest 25th. Good. So on Wednesday, if you have trouble with some questions, I will help you guys. And as always, you know that that I'm very well aware that some people did not listen to my advice, and of course posted my exams or cheated. I'm very well aware that it happened in this class as well. The final exam will address that. So again, guys, do not, I mean, one thing, you see, I'm forgiving you. Hope you understand that. I don't particularly, even if you cheat, I don't particularly want to get involved. It's boring to me and taking my time. But if I get to the wrong state of mind, and you encourage that, then I will go after some of you. Yes, and that happened last semester. I caught 8 people. Understood? We'll see how many I'll catch this time. But hopefully I will not need to even bother with it. So the questions, I tend to like to ask 10 questions that are regular and more or less 2 to 3 questions that are extra credit, right? The extra credit questions might be difficult. There is no reason that you have to get 100, guys. Right? Just do the questions that you understand well, right? I mean, you already have a good grade for the second exam. You will probably have a good enough grade for the first exam. There is no need to, to get 100. If you cannot answer something, move on, answer the other questions. It's perfectly fine. Understood? All right, so then guys, let's continue with the lecture. We would at least try to cover a little bit of integration. It's a bit, I was hoping to get to chapter 6 and through, and I'm sorry to disappoint you in that regard, unless of course you want to continue past the semester. So we started speaking about continuous random variables, and those are just sample spaces that can take a continuum of values. As for instance, we gave the example of a strand of hair. It can be cut anywhere from the root of the hair to the point 1, to the very edge of the hair. Yes. So we understand, I hope, guys, how integration comes into play. So I can approximate the variable by a sequence of discrete variables. So this variable, let's say, can take values 1 quarter, 2 quarters, 3 quarters, and 4 quarters, for instance, right? And then we say that any cut that happens in this region will be interpreted as 1 quarter, any cut in this region as 2 quarters, any cut in this region as 3 quarters, and so on and so forth. Yes. So by making the discrete random variable, by allowing it to have many pixels, those are like pixels here. Can you understand what I mean by pixels? You see that here there is this discrete sense that, I don't understand the notion of continuity over this region when I approximate by discrete. So it's either 1 quarter, 2 quarter, 3 quarter, or 4 quarters. But if I increase the number of points that a discrete variable can take, it will create the illusion of continuum. Yes. So if the columns here are very, very thin, tremendously thin, then the skyline will be a curve. In this case, the skyline seems to be the line y equals to 2x. I just kind of made it so. Yes. So the integral from a to b to x dx, what is that thing? It's just the rectangles or the skyscrapers that are very thin, whose skyline is 2x and whose width is dx. That is giving you the discrete variable sense, right? So this is just summing them up. So we just add up all of them. So the height of this function is such that the area represents probability. I hope that's clear, guys. So we, by design, create very thin histograms so that their area will represent probability. And this is the definition of a continuous random variable. So it's just any random variable with a continuous skyline. I call it a skyline. This is called a density function. So that the integral, so the probability of B will be the integral. Yes? And we solved a few of those questions here. We realized that, for instance, the probability that a discrete random variable takes any particular value could be non-zero, but the probability that a continuous random variable takes some number A is 0, right? And that it means that essentially that every time there is an outcome from a continuous random variable, you will not expect this outcome to repeat, and therefore the probability is 0. It's a miracle. Good? But there will be, every time the random variable generates a new miracle, something that never repeats. And then we spoke about how to interpret the Barber density curves here. We see that this Barber cuts short, this Barber leaves the hair long, and this Barber sometimes cuts short, sometimes cuts long. He's still a novice barber, doesn't really know what he's supposed to do. Right, and then this is what you will see happening if you get those haircuts. So here is our first, hopefully simple question, guys. Suppose that x has the density function, probability density function given by cx squared, where x is between 0 and 2 and 0 otherwise. What do you think must be the value of c? Right? What's the value of c, guys? Very simply, we know that the probabilities add up to 1. The probabilities in this case are areas of very tiny rectangles whose height is the density function and width is dx. So 1 should be the integral from -infinity to infinity of the function. But in essence, we can drop away everything in this integral except for 0 and 2. Only the interval from 0 and 2 is significant. So this integral has to be equal to 1. Do you agree, guys? And this integral is c over 3x cubed from 0 to 2, and we get 8 over 3 times c is 1. So c is 3/8. It has to correct the area so that it equals to 1. And then we can calculate the probability that x is between 1 and 2 to be the integral from 1 to 2 of this function, and you just get 7/8. Here is another example. The amount of time a computer functions before freezing up is a random variable with this density function. Find the probability that the computer functions between 50 and 150 hours. So first we need to integrate from 0 to infinity to figure out lambda, because this integral from 0 to infinity ought to be equal to 1. You can see that this integral then implies that we have lambda times 100 is equal to 1. So lambda is 1 over 100. Just basic integration. Do you agree, guys? So far, no problem. You let me know if I move too fast over something and I can repeat it. So the probability that x is between 50 and 150 is then, you see, once I know the lambda, I can just calculate this integral. And I just get minus e to the minus x over 100 from those values. And the answer is simply e to the minus 1/2 minus e to the minus 3/2. Then finally, guys, remember we spoke about cumulative distributions. And in the discrete variable case, I could never truly understand what's their point. But in continuous variables, they play a very major role. Okay, because look at it. Look at this function, guys. The cumulative distribution is defined. The cumulative distribution at a is defined as the probability that x is less than or equal to a, which is this integral from -infinity to a of f of x dx. Do you recognize this function from calculus, guys? It is the function from fundamental theorem of calculus. In other words, its derivative, the derivative of this function has to be little f of a. The derivative is little f of a. The derivative of the cumulative distribution is the density function. Does anyone need to be refreshed on the fundamental theorem of calculus? If you do, guys, definitely stay with me after class. I can give you a short overview of that. Yes? I don't want to be taken far from the topic currently, but please, if you don't know it, we can have a discussion of it. It's not difficult and we can remember. This function is the antiderivative or an antiderivative of little f. Here is, I actually even give something here over here, guys. See, I said after class, but what do I know? It's actually in my notes right over here before our eyes. What's happening when you integrate, guys? By definition of the derivative of this function, this is the definition of the derivative. Do you still recognize it? It's capital F at a plus h minus fa divided by h. Now, this is just an integral. One integral minus another integral, and that becomes what? That becomes the interval from a to a plus h fx dx times 1 over h, right? So guys, what happens if h is going to 0? This quantity is essentially what? Look at it. If h is going to 0, the curve is continuous. Look at it. It looks like an integral, like a rectangle. Do you agree? If h is going to 0, eventually all the altitudes at any x in this interval will be indistinguishable from this altitude at a. Yes, so that integral here can be replaced by simply the red elevation times the width. In the limit, it's the same. You can see it's not the same for this picture, but as h goes to 0, you can see that it looks more and more like a rectangle because the function is continuous. So what do we get here? We get that this is 1 over h, f of a times h. This is the integral. The area under this curve is essentially the area of this rectangle. Yes, the rectangle of height fa and width h. So then the h's cancel and we see that this is f of a. So again, we are seeing, and we can talk about it at longer, well, we can talk about it through the office hours, guys. The derivative of cumulative distribution is the density function, is this skyline. Good. So here is the question, guys. Here are some examples. If x has the probability density function little fx, find the density function of y, where y is twice x. That's where it can be very useful. Okay. So you understand, guys. So we know that x is continuous random variable. Okay. And we know that it has density. It has pdf little f x. Okay, and y is equal to twice x. Find f sub y. Do you understand? I want the density function of this newly distributed random variable. Now, how can I go about doing it? Let's look at it, guys. So I can begin by considering the cumulative distribution of y, and I want to take its derivative, right? So the cumulative distribution of y is going to be, by definition, the integral. Well, it's going to be by definition, before we say the integral, by definition, it is the probability that y is less than or equal to a. Do you agree? Which is the probability that 2x is less than or equal to a, which is the probability that x is less than or equal to a divided by 2. Yes, which is what, guys? Look at this thing. This is just the cumulative distribution of x, but evaluated at a divided by 2. Do you see what I'm doing, guys? I moved from the cumulative distribution very easily for y to the cumulative distribution of x. And so by the fundamental theorem of calculus, I just have that little fy at a is the derivative with respect to a of fy at a, which is the derivative with respect to a of fx a over 2. And this by chain rule, guys, this by chain rule is little fx evaluated at a over 2 times 1/2. Yes? Do you see that? So I was able to right away figure out a new density function from an old one. That's a very, very useful transformation. Let's do another question like this. Here is a more particular example, guys. So suppose x has a PDF given by 1/2 if x is between 0 and 2 and 0 otherwise. I want to understand how 1 over x is distributed. Okay? How 1 over x is distributed. So this is how we work on this problem. So first, guys, we begin with this notion. So first of all, if x is between 0 and 2, then y, which is 1 over x, must be bigger than 1/2 and less than infinity. Do you agree? X is between 0 and 2, so y is between 1/2 and infinity. That's the outputs I can have, because if x can be a value close to 0, y will be then a value close to infinity. If x is a value close to 2, y is a value close than 1/2. Correct? So then what may I do here, guys? So then I can look at the function at a, once I know what's the range of y. I look at the cumulative distribution of y at a, which is, I mean, I can also let it be less than a or equal to a. You remember that probability that the continuous random variable equals a is 0, correct? So I can be rather careless about less than or equal or less sign, because a, the probability of something equaling a is 0. So what do I get? I get that this is the probability that 1 over x is less than a, which, guys, by taking reciprocals is the same as probability that x is bigger than 1 over a, which is the same as 1 minus the probability that x is less than or equal to a, which is 1 minus capital Fx at 1 over a. Are we good so far? All right, guys, confirm that you are still alive, right? Yes, good so far, like Y or something that I see that you understood. Yes, if anything unclear, guys, I will try to, maybe you think it's useless, pointless by now, right? Like nothing makes sense, but I hope you follow everything I'm explaining. Good. So this is what we have. And then I take the derivative with respect to a. Derivative of this function with respect to a gives me the density function for y. And this formula, I can actually take derivative with respect to a. And what do I get? I get that this is 1 over a squared times fx 1 over a. So what does it tell me right away, guys? Look at it. 1 over a squared. that means I can convert it. There is no reason why I can use a or not and not y. So this is 1 over y squared. And what is this function? This is the function simply 1/2. This function is 1/2. Look at it. Wherever it's defined, for any values where it's defined, it's 1/2. So it's 1 over y squared times 1/2 for any y between 1/2 and infinity and 0 otherwise. Good? If you understood, guys, I want you to try to do the next question. So the density for x is e to the minus x for any x between 0 and infinity. And I want you to find the probability density function for y, which is equal to e to the power of x, please. See if you will be successful. I want the exponential of that random variable and how it's distributed. All right, guys, let's do that together and you will help me with some of the key steps. Okay? So again, x has PDF, let's just call it f, x to be equal to e to the minus x if x is bigger than 0 and less than infinity and 0 otherwise. Okay, find PDF for y equal to e to the power of x. So here is where we begin. We say capital F y. If you prefer, you can use y here. Doesn't matter. Let's say, just I hope it's not confusing. This is just a symbol, and this is the variable, and that is the probability that y is less than or equal to little y, which is the probability that e to the power of x is less than or equal to little y, which is the probability that x is less than or equal to what, please? What do I put here? If e to the y is less than or equal to y, then yes, then what is x? So by the way, here I can see the values of y. If x is 0, we get 1 and to infinity, right? So y is varying from 1 to infinity. So help me with this, please. ln y, very good. So here we have ln y, yes? And what is this? This is the cumulative distribution with respect to x at ln y. That's the cumulative distribution is serving as the link between the distribution for f, for the y variable, and the x variable. So then I can take the derivative. Then let's take the derivative. And here I have little fy of y. And what do I get here? Here I get f evaluated at ln y times the derivative of ln y, which is 1 over y. Which is what? What is f of ln y? You can see over here, it is e to the power of minus ln y times 1 over y. And what's e to the power of minus ln, guys? That's the same thing as 1 over e to the ln, and that's the same thing as 1 over y. So the answer is 1 over y squared. Do you agree? The answer is simply 1 over y squared, which means that the distribution, the density function for y is given by this formula. It's given by the formula 1 over y squared if y is bigger than 1 but less than infinity, and 0 otherwise. So it's distributed as one reciprocal of the square of y. Good. Here we have the same thing, 1 over y squared. And I hope you understood this part, guys, because we're moving to the problem of defining expectation. What's the expected value if we are dealing with a continuous random variable? So here is the situation, guys. We can define the expected value for a continuous variable by using discretization, by approximating with discrete random variables. Those we understand pretty well. Yes? That's what we do all the time, guys. So what do we do when we are trying to construct a picture, like a video picture? We build it out of pixels, right? Very simple pixels. They change lights in particular ways, and the combination creates very complicated images. So that's what we do here as well. So what should be the pixel? If I want to understand the expected value of x, then I can imagine that it's a discrete random variable. Basically, if x happens, if x is equal to x, that means what? We can imagine that x happens if it's x or x plus dx, somewhere in between here. So there is a small width. I make a rectangle that is very small, and then it looks like x happened. Make sense? And so then we have a random variable that has discrete segments with the form x to x plus dx and the height. And what is the summation? The summation over all such x and the probability multiplied by the probability. The probability is the height of the function here. That's f of x multiplied by the width. That's the probability. So fx dx is the probability. X times the probability, the summation will be giving me an approximation to the expected value. That corresponds in the limit to the integral from minus infinity to infinity of x times f of x dx. Did you understand what I said, guys, or zero of it understood? I have a feeling somehow that not enough. Here is what I'm trying to say, guys. Here is my interval, right? My random variable can take values between, let's say, A and B. Yes? Here is that curve. That's the density curve. So that's this is variable x can take values here. So if so, then what can I do here? I can imagine partitioning it into many small segments. Right, so this segment is, they just give this segment the label x. So do you see basically what I'm saying is that, guys, I approximated, the actual random variable can take values anywhere on the black line. But my approximate version can only take values on the red marks, right? So only the red marks can be taken place. And what I will have is, I will have many red marks. You understand? Just cut it and cut it and cut it until you have tremendously many red marks. Good? So the width here is in general dx. Height is fx. So this region is approximately the probability. So basically probability that x equals to x is approximately x times, it's approximately, sorry, f of x times dx. Make sense? And when I say a probability where x equals to x, of course, I mean, if it's a continuous variable, that cannot happen. But if I make it in red, then I created a discrete random variable that takes only the red notches. Right? Those are the only values that can be taken by this variable. And I just presume that they are very close together. So dx is just a very, very thin region. Good? So that's the probability. So then how do I, maybe you can prefer just take it to be with a hat. It means it's an approximation to x. Capital X represents the random variable, the continuous random variable, right? Capital X means that here is perhaps the difference. So you see, guys, so I can, the random variable x can take values in here, for instance, right? But the approximate random variable, this one, this is an approximation, right? It can only take those values. So far clear? What my red x can only take the discrete values. And those discrete values are going to be very close together. Now, what's the probability that, that the red x takes this particular discrete value? Its probability is very closely simulated. That's how it was constructed. Remember, we go backwards. This area is representing the probability. What is that area? If dx is very small, it's just a rectangle that has width dx and height f of x. So that represents the probability that discrete random variable takes this value. Yes? And what's the expected value of red x? Expected value of red x is then summation over all the x that it can take over those red notches, and then the value x multiplied by the probability fx dx. But you look at this summation, guys, and you recognize this is a Riemann sum, right? It is a Riemann sum for the actual continuous random variable, and that would be in this case from a to b, x f of x dx. You all remember Riemann sums, guys, yes? So you just look at this thing, and what is a Riemann sum? It's a sum of areas of rectangles, nothing more than that. Yes, I'm not speaking, guys. I hope you are not too rusty on integration and those ideas. Yes, you understand that you should think of them very simply. What is an integral? It's just a fancy way of summing very, very tiny areas of rectangles, adding them together. Now, the way the skyline of the continuous random variable was constructed, remember the way I presented it, is that we have very thin towers. And the towers, if they are thin, they have very short base. That's why I label it as dx. It's the difference between the two notches. Yes? So the probability there, this particular column is f of x dx, and multiplied by the value x gives you the probability times the value, like we did for expected value in general. And then I push it to the limit. I make the red notches very, very frequent. If I make them more frequent, the entire black line will look like it's covered in those red notches. And that becomes a better and better approximation to the actual expected value of the continuous random variable. So we see that we can arrive at this definition very quickly. We see that that the definition for the expected value of x should be the integral in general from minus infinity to infinity x fx dx. Minus infinity to infinity means just that the random variable might potentially be able to take every single possible number, right? Every real number. Good. So very quickly, guys, let's calculate expected value of x when f of x is 2x for values between 0 and 1 and 0 otherwise. So that was my barbershop example, right? The first example we began, that's the distribution. So let's see what happens. If I multiply x times f of x, I get 2x squared. And I integrate it from 0 to 1, and I obtain 2/3. In other words, on average, this particular barber cuts the hair 2/3 away from the root. Yes, so it's a little closer to the end of the hair. All right, guys, here is the next challenge, guys. Would you like to try it yourself? So in this case, the density function for x is given to be 1 if x is between 0 and 1 and 0 otherwise. Can you calculate the expected value of e to the power of x? Not of x, but the of e to the power of x. All right, guys, what's going on? Let's do it together, I guess. So here is the situation, guys. First of all, we have to, the way we did it before, we're gonna do it maybe in 2 ways, guys. So the way we did it before is we need to actually obtain the cumulative distribution for this variable, and from there the density of that variable, and only then can we take the expected value. Do you agree? So I mean, here I have the density of the function of the variable x, but I don't have the density of e to the x. So then what do? We let y equal to e to the x. The cumulative distribution of this y is, you just go here. It's the cumulative distribution of x evaluated at ln a. Now notice, what is a? A is between 1 and e, right? If x is 0, then y has to be 1, and if x is 1, y has to be e. Yes, so this is the situation here. And then I take the derivative, and what do I obtain? I obtain the derivative is simply 1 over a, that's the inner function, and then this function evaluated at ln a. Now, wherever it's evaluated at ln a, where a is between 1 and e, that will give us 1. So that's just simply 1 over a. So that means that the density function is 1 over y, from 1 to e. And so the expected value of e is the integral from 1 to e of y times 1 over y. And that ends up being, the expected value is e minus 1. Yes? The answer is e minus 1. How many of you obtained that number? No? Yes? Amazing, right? So that is the one way to integrate it. I would like you to actually observe, guys, what happens if I integrate straight away. If I just take 0 to 1 of e to the x, and the function is 1 dx, I still get e to the 1 minus e to the 0, which is e minus 1. Isn't it interesting? I get the same result without doing that intermediate process of first finding the density function for y, and then taking the expected value thereafter. Now here is another example, guys. So the density function is 3x squared if x is between 0 and 1. And we want the expected value of root of x plus 1. Yes? So what do? We first set y equal to root of x plus 1. You see, guys, you understand what I'm trying to accomplish? I mean, by definition, expected value of a random variable is the value a random variable can take multiplied by density function and integrating that over all possible values the random variable can take. You agree? That's the way we defined it. This is here the definition. Do you see it, guys? If I have a random variable, I just multiply its value corresponding to the density function and integrate it. So again, here I'm given the density of an entirely different random variable, not the one I have to calculate expected value for. So then by definition, I think, well, let me try to find what the density function is. And what is the density function? Well, y equal root of x plus 1. Then x is between 0 and 1. So what we have is that y is between 1 and root 2. And then the cumulative distribution of y is where y is less than or equal to a, which is root of x plus y plus x plus 1, sorry, less than or a. And that means that x is less than or equal to a squared minus 1. Which means that the cumulative distributions are related this way. It's the cumulative distribution for x at a squared minus 1. I then take the derivative. You see how I'm using cumulative distributions? I just know by fundamental theorem of calculus that derivative of cumulative distribution is density function. And I can just move from density function to cumulative distribution and back and forth. Cumulative distributions, because they're antiderivatives, they play a major role in continuous random variable theory. So I take the derivative, and what do I get? I get 2a, the derivative of the inner function, times the derivative of the outer function, which is my little f, at a squared minus 1. And what is that formula? Look at it, guys. A squared minus 1, it's over here. I plug, instead of x, I plug a squared minus 1. So it would be, and then the 2a will together will make it this function. It's 6y, y squared minus 1 squared, for y between 1 and root 2. And this is the integral I have to calculate. It's a bit ugly of an integral, but doable, and this is more or less the answer is about 1.320. Yes? Now again, I wanted to show you guys that if you did not actually bother with finding if you did not bother, that's actually a good calculus 1 question, right? If you did not bother doing the conversion and just straight away multiplied the new function, in other words, root of x plus 1 by the density of x, you get this integral. This integral will equal to the same exact value that is obtained if I find the density function. Exactly the same thing would happen. Here you see. But in this form, it's one of those U substitution integrals that you learn about in calculus 1. Yeah? Just the other day I was talking about this. And the expected value, look at it, I can just use U and I convert it exactly to the same thing that I was integrating above. Exactly to the same thing. Here is the thing. And here is the thing I obtained by U substitution. And then, guys, we have the following theorem that I will try. You see here I present you one type of proof using I present here a proof using double integration from Calc 3. But we can actually see that this must be the case much simpler. Okay, maybe I will show you the simpler reason. Do you want the simpler reason or do you want Calc 3 reason? All right, let me try the simple, guys. What is really happening here? You should know. All right, I'll try this to see. It's very simple, guys. Let me see if I will be able to explain it well for you. All right, so let's see what are we doing when we calculate expected value. Again, we can go back to the discrete case. So here is the density function. This is the continuous random variable x. And here is the density function. What do you do, guys, when you try to analyze an image? You break it into pixels. Same thing you do with the random variable x. You break it into the discrete version of x. It's a discrete version of x. You agree? So in other words, this red x can only take the notches, the values at the notches. Okay. What are we truly doing when we are applying a function? So we want to understand what is the expected value of gx, where g is some function. What is the G, guys? What is the G doing? The G is just relabeling those x's, right? So what happens, how is the G acting? The G is taking this value and making it into this value. It's just like before, it's a relabeling. Yes? What do you do when you calculate expected value, guys? You just calculate the average of your scores, correct? You calculate the average of your of the G's. Now, how many times are you going to get a particular G of X? So it's just the same score. It's the same score G of X multiplied by the probability of getting it from this X. So it's by the density function F X dx. That's the probability of getting this this particular score. You need to get this X. I should say this red X maybe. So this red X, this is this area is little fx dx. It's the probability of getting this particular X, right? So you get gx, but with what probability? With the probability of if you get X, you'll get gx. So that's the probability of getting that gx. Right? What do you do, guys? I hope you remember what you do with expected value. You multiply the scores by the probabilities of getting them. You agree? All the scores by the probability of getting them. If you understood why that worked in discrete case, why you did not have to find the probability mass function for gx when you did it in the discrete case, you should understand why that should be the same for continuous case. This means the probability of getting that. Well, let me actually do it. Maybe I should color it in red. So that red means discrete, black means continuous. So that basically, so this is gx times fx dx, and I add up over all the x, and that should give me the expected value for g. For g of x of the red, and that is approximately the same thing as the integral from minus infinity to infinity of gx fx dx. That's for the continuous case. I just get a Riemann sum here. So in my notation, guys, red X is discrete. It's an approximation, right? Red X is discrete. I color G in green, but that's just a relabeling. That's not changing anything. I just relabel those values. So you have to understand two things, guys. If you understand change of values in the discrete case, why in the discrete case, you have to, of course, guys, I hope it's in your mind. Do I need to re-explain? Do you remember how expected value was explained for the discrete case? Yes, you have to truly understand the mechanism, because if you do not, then it's a pointless conversation. In the discrete case, do you understand the expected value? Yes. And do you understand what happens when you relabel the variables, right? So remember the discrete case, guys. So you have a sample space, right? And then you just relabel, you have values 1, 2, 3, 4, 5, and you just relabel them. So that's x of 1, that's x of 2, x of 3, x of 4, x of 5. They might be some of them equal. Do you agree, guys? I mean, x of 1 might equal to x of 5, right? And then you have, here you have probability. So this has probability P1, this has probability P2, this has probability P3, P4, P5. Now, what happens when you apply a function? When you apply a function, you do further relabeling. If you apply a function g, then it will become gx1, gx2, gx3, gx4, gx5, right? It's just a further relabeling, guys. There is no mention of one-to-one. I mean, some of those arrows might lead to the same numbers, right? Either the black arrows or the orange arrows, right? They might create same numbers. What are you doing when you calculate probability? When you calculate expected value, you just average the values of g. Now, how can you average them? You can average by first combining like values. It's the same value and then tracing all the inputs that produce the like values. Or you can just keep them isolated and it would work all the same. You agree? Do you understand what I mean, guys? Yes. So I mean, I can draw you more concrete examples if you have to, but I hope we talked about it before, so I hope you remember, right? What rearrangement of summation? That's pretty much all that happens, right? How was the score created? Was this score created? I mean, I can forget. I can just group them based on the score, or I can keep track of where the score came from. Did it come from outcome 1, 2, 3, 4, etc.? Yeah. Understand or not at all? All right. I hope you do, guys. You have to think very simply. What is expected value? Go back to the idea of it, the definition, the average, right? If you do something again and again and again, you make something a habit. Like you buy a lottery ticket by habit. It could be that you buy a lottery ticket and you get happy and lucky and you get millions of dollars. But if you continue buying lottery tickets every day, every hour, if you continue doing that without stop, what would happen is the same as if you're paying 99 cents on the dollar, right? If the ticket costs $1, maybe you're just paying 99 cents for it or even more. Yes, it's like you're regularly buying something without it becomes very regular. So that's what expected value is representing, that average, that regularity. And I can calculate it by tracing my payoffs, just by grouping by different payoffs. Remember, we had column 1, column 2, column 3 type of thing, right? By grouping by payoffs or by grouping by outcomes. And it doesn't matter how I add the columns. I will produce the same expected value, correct? I hope you remember it, guys. I spoke about it at length from before. If not, we can return to it. The point being is you can calculate expected value in several ways, either by finding the density function or by just working with the density function of the initial random variable that was already given. Here is what this is saying. Let's try to calculate, let's use this theorem to calculate expected values, guys. A stick of length 1 is split at a point x that is uniformly distributed over the interval 0, 1. Determine the expected length of the piece that contains the point t. So here is a point t, you see? It's over here, it's placed somewhere on this number line, and you cut anywhere randomly between 0 and 1. So 1 means, if the density is 1, it means that all rectangles are of the same elevation. Do you agree? You can see that one, guys, the elevation of all the rectangles the same means that cutting everywhere is equally likely. So what's the expected value of the length of the piece that contains point t? So clearly the length with respect to t would be what, guys? If I cut it at the point x, where x is less than t, the length is 1 minus x. Do you agree? If I cut at the place below t, it's this length that contains the t, so it's 1 minus x. And if x happens to be, let's say, over here, then it's above t, then the length is simply x. So the expected value of LT, of this function with respect to t, is what? Is the integral, t is the point where I need to switch from one function to another. So it's the integral from 0 to t of 1 minus x dx of this function, plus the integral from t to 1 of x dx, and that's of this piece. And when I calculate the integrals, I obtain 1/2 plus t times 1 minus t. And this is maximal when t is equal to 1/2. T times 1 minus t is biggest when t is 1/2. In other words, if I place the point in the middle, then that will make the average length of stick as big as it possibly can be. Yes, guys? I'm a bit tired and I don't know. I mean, I'm hoping you follow what I'm saying. If not, guys, you let me know. What's the point of me blubbering on without any sense? Do you understand what I was saying, guys? Do you understand when I say columns, or you think, well, let him speak, the lesson will be over in 13 minutes? Confirm if you understood what I said, most of it, some of it, all of it. I mean, it bothers me tremendously if you don't understand my column analogies that we spoke about, right? So we have the outcomes, we have the x payoffs, and we have the gx payoffs, and we can use any one of those columns to sort the sum. Remember with the way we talked about it, right? So I can always go back to the discrete case. If I understand the discrete case, I truly understand the continuous case. It's not more difficult, right? I think of continuous case as a discrete that has outcomes that are very near one another. Just like I think of watching a movie when I'm watching lots of frames changed one after the other, right? A cartoon, you have many frames flipped and it looks to you like a movie. It's the same idea, right? So a discrete random variable can approximate continuous random variable very well. And therefore I can learn about continuity from the discrete case. That's what we do. Right, so in essence, the reason this integral works, the reason this formula works is because I can convert it to the discrete case, where I realize that in the discrete case, it's just a matter of changing the order of summation. Yes? You can, of course, be fussy about it and require very rigorous proof, and that involves measure theory, right? So you can become worried that the approximation isn't good and whatnot. Good. Here is another example, guys. The place where an accident occurs is a random variable x with probability density function, 2x if x is between 0 and 1, and 0 otherwise. So there is it's like Ocean Parkway, if you know what it is. And in some places, it's very likely there would be an accident. And then where along this highway should you place a hospital? What's the best place to position a hospital so that the hospital is as near as possible to the accident? You understand? You want to minimize the expected distance to the accident on this highway. Let's say that's your goal. So how do we do that? So you see, here is the situation, guys. The accident can occur anywhere on the road, and this is the density of the random variable where it happens. And I decide Q to be the point at which I build a hospital. Now, what's the expected distance to Q? Well, look at it. If x is below Q, the distance is Q minus x. And if x is above Q, the distance is x minus Q. Do you agree? This random variable represents the distance. And now what's the expected distance? Let's calculate the expected distance. It's the expected distance, well, in this situation, below Q plus the integral above Q. Right? I just break this integral into two parts. And then I calculate it, and what do I get? You see, this is just a calculation. I get 2/3 minus q plus 2/3 q cubed. And I will let this be e of q. I'm going to optimize this function. I want to find a minimum. So I'm using an optimization from calculus, if you remember that, guys. Yes, I want to find I want to make this minimum. So then I take the derivative of this function and set it equal to 0. I obtain minus 1 over root 2 and 1 over root 2. Now minus 1 over root 2 is already to the left of 0, but it's useful nonetheless to understand the behavior of the derivative. So how is the derivative behaving? Look at this. This is the derivative. Now, if q is below both numbers, it's positive derivative. Then here it's 0, the negative derivative, then positive. So look at it, negative, then positive derivative means I have a minimum at 1 over root 2. So the place of the hospital should be 1 over root 2 along the length of my highway. Yes? So I move from 0 to whatever that number is, I'm just normalizing the highway. That's where I should place my hospital to be able to assist as fast as possible. Clear? And here is another example, guys. It's a sort of when should you leave your house to get somewhere, right? So you have an appointment, and if you're early, you are penalized. If you're late, you're penalized. When should you leave your house? Yeah, I mean, when should you leave your house? I will actually let you think on your own, guys, right? Think about it based on the information of this problem. I want to move to the next topic, okay? It's a bit interesting, even though rather useless without a lot of extra information. I need to know the transport, I need to know how long it takes me to get there, you know, and the density function, and a lot of information that I usually, well, I mean, you can have it actually. It's also useful ideas, but you have to be able to gain that information. So Google does that, I suppose. Let's just look at a few properties, guys. If A and B are constants, then just like before, the expected value is linear. So that's very obvious because, well, the expected value of ax plus b is just this integral, and this integral is linear. Now, variance is equally naturally defined as the expected value of the variable minus the average squared. And you can observe that the variance is, as before, the expected value of x squared minus the square of the expected value. And variance of ax plus b, very naturally, if you shift the random variable by b, you're not changing the distance from the average. You change where the average is, but not the distance, yes? If I move the distribution left or right, I will have a different average, but not, I'm not changing the shape of the distribution. So on average, the distance from the average remains the same. So clearly, in variance, this constant term should play no role. And if you multiply by a, that does play a role. It will be a squared, because multiply the distribution by a, the x by a, that kind of stretches the values by a factor of a, and will make the variance stretch by a factor of a squared. All predictable and all easy to calculate. Yes? You understand what I'm talking about, right, guys? Because I'm measuring on average how far away are you from the average. So if you multiply the points and you make them like our space is moving apart, you make the points a factor of a apart. On average, the variance will be a squared apart, because the average is the square of the distance. So all those things are expected. Yes. So here, our last task, guys, is to calculate for this random variable. Please calculate variance an expected value. You see, here is your random variable. I want expected value and variance. Can you do that and tell me the numbers? Thank you, Nora. All right, that's two people calculated expected value. Guys, expected value, that's the quickest possible thing. Thank you. So what's the expected value, guys? Very quickly, just it's this function multiplied by x and integrated. It's 2/3. Now, how do I calculate the variance? Well, I mean, I can do it directly. Variance is simply x minus 2/3 squared times 2x, or I can just calculate expected value of x squared, which is this thing. And from that, I subtract the square of this thing. So I get 1/18. Yes? This is all easy, guys. You can carry the integrals, but do you understand why that's what those things mean? That's what I hope for. Right, the column analogy. So what's the discrete expected value? Why the function of a discrete random variable allows us to not change the distribution. Those are important ideas that you have to make intuitive. They're very intuitive, actually. Yes? All right, guys, yes or no? I mean, what can we do? I mean, so again, I would like to remind you, if you can join on Wednesday, we will have one more lecture. I will try to send you the final exams before Wednesday. I will try to even do that tonight. I do not know if I'll finish, but I will try tonight. I'm almost done grading your first exam, so I'll send it soon as well. And yes, it's gonna be due on May 25th. That's the latest I can have. Any questions? Are you gonna come on Wednesday? Yes, midnight, I suppose. Are you gonna come on Wednesday? You better, right? All right, guys. So if you want a what, when, where game, we can play one. If not, goodbye. Take care.